Let's take a look at the refraction worksheet, right? We should have already opened that up. You don't need to print it off or whatever, right? But open that up and look at those questions. Hopefully you've already got those figured out, but I will look at them with you. Before we start on those, a nice way to think about light as it's bending is to think about like a car driving from one surface to another. So let's say I've got concrete here, like a regular road, and mud here. So if the car hits it at 90 degrees, right, it should just continue on straight. You should be okay, right? Now, if you're going really fast, you're not going to be. But if, on the other hand, you hit it at an angle, right? Imagine your tires are right here, and you hit this thing at an angle. Concrete, your tires are going pretty good, but when they hit the mud, think about what's going to happen there. Dora the Explorer type. This wheel is going to hit the mud first, and when this wheel hits the mud, it's not going to move very well. So if it slows down and the rest of the car is still going, it's going to turn that car this direction. And then it's going to travel through here, and then as it gets to the other side, now this tire again is going to hit the concrete first, and now that tire is going to start going faster, and it's going to pull it the other way. So you're going to bend towards the more dense, like mushy stuff, right? And away when you go to the place where you got better traction. So you can think about that the same way that light is you have a less dense media, a more dense media, and a less dense media. Light's going to bend the same kind of way. And as we get into lenses and stuff like that, I think that can be a helpful way to think about that. All right, that's also one of your quiz questions. If you're watching the video, you get the bonus free quiz question. So number one, what happens to the direction of the light rays as they pass into different media? They bend. That's not very hard, right? That's the fish tank effect, right? You stick your arm down in the fish tank, your arm jumps to the side because the light bends and your eye traces back a straight line. Use the data for an equation 2. So equation 2, that's the equation in your book, right? And that equation is that the refractive index times the sine of the angle at that in that substance is going to equal the refractive index times the sine of the angle in the other substance. Keeping in mind, air is 1. Right? We just basically define air as 1. So if we do that, when I was going through the last video, we had one that was 45 and 62. So when it was in the water, it was 45. So if I say the N of the water is at our 45 degrees, it's going to be N sine of 45 is going to equal air, the sine of it in the air, which is 1 times the sine of 62 degrees. And if we do that, that gives us a refractive index of 1.24, right? 1.24, yeah, 1.245, so 1.25, right? So that's the refractive index. That's not really what we're supposed to get. We should have gotten closer to 1.3 on that. Water is about 1.3, so that's pretty close. My other set of data was 10 and 18. So let's see, 1 times the sine of 10. No. That part should be on the bottom. Sine of 18 divided by sine of 10 gives us 1.7. Ooh, that's too much. That data must not have been very good either. Don't put in the 1.33. That's theoretical for water. I put that in as one of the quiz things so that people who just Google, I don't know, what's the refractive index of water, and they Google it are going to get that wrong. So based on my terrible data, we got 1.24. When light passes from a media with a high refractive index to a media with a low refractive index, which direction does the light bend? So it's in a high refractive index, it goes to low, it's going to bend away from the normal. When you go from more dense to less dense, you bend away from the normal. When you go from less dense to more dense, you bend towards the normal. When trying to find a fish, would a bird such as a pelican dive into the water in front of or behind the fish that they see? So this one I think really helps to just draw the two. There's my pelican. Here's my fish. This is more dense. This is less dense. So as the light comes up, it's going to bend away from the normal towards that pelican. But the pelican's going to trace that line to the fish here. So the pelican's going to see the fish here, but it's actually over here, right? Because the light comes in wherever, the light bounces off of the fish. The light that the pelican's going to see is going to be the light that comes up here and bends this way. So the pelican's actually going to see the fish in front of where the fish actually is. Right? That's not where the fish actually is, but that's where the pelican's going to see it. So it should dive behind the fish, not in front of the fish. right? Again, that one's one of the quiz questions. So hopefully that quiz is nice and easy today. Lots of cool stuff with reflection, actually. There's all the lenses. That's how rainbows get formed. That's how you can be invisible to fish, because if you are sitting like right here, right, and if we imagine the light, if you're low enough, then there's a total internal reflection. So if you imagine the fish is trying to see you, at some point you get a total internal reflection and it goes invisible. So unless you get so high, the fish wants to be able to see the whole horizon, but it can't see down so low because of the refractive index. So I can't remember, well, it'd be off of the 1.33. I can't remember that calculation off the top of my head, but there is a angle that as long as you're below that, the fish can't see you anymore. And you can actually, well, no, I don't think you'd be able to see the fish still there, but they can't see you because that light can't get in there. And you get total internal reflection. You can do all the stuff with lenses and distortion, and there's all kinds of cool stuff you can do with refraction, but we'll tinker with that stuff a little bit more next week too.